Chapter 5, Section 4.3 and 4.4, Part 2 video. We're continuing on looking at exponential properties compared to log properties and so forth. So the first thing we're looking at is exponential properties. So we're 10 to the 7th divided by 10 to the 4th. And if you remember, if you got bases of being divided, you subtract. So it's 10 to the 7 minus 4, which is, I can do that, well, which is 10 to the 3rd, right? Now, same thing that we done. If you got a log, that's a common log, and the of is the same base, and it is, then it's just the exponent. And then same thing here. It's just 4. That's a property, okay? Now, when you look at this one, this is ain't different. So should just be 10 to the 7 minus 4, which would be, if I can do that correctly, 10 to the 3rd. So 10 to the 3rd. But I think they've left off a 10 somewhere. It says, well, let me look at something real quick, because I think when I looked at the answers on this, they just done it as 3, but they did. They didn't put 10 to the 3rd right there. So just that's wrong on their part. So it really should just be log of 10 to the 3rd, right? But they're going to just put 3. Note that you're going to need to put 3 if you're going to get the answer correct on this one, okay? All right, so solving exponential functions. Why are exponential functions coming up into properties of logs and so forth? Well, the reason they are is when you go to solve exponential functions, you're trying to get their bases to be the same so you can set their exponents equal to one another, right? B to the x equals b to the y, so, and if that, so x equals y, right? If you can get that, well, there's no way that I could get, and let's just put there's a power of 1 on that 8. There's no way I can get 7 to be a base of 8 and 8 to be a base of 7. So how do you do this? Well, you take the log of both sides, right? So the log of 7 to the x equals log of 8. And so I'm going to show you how to do this by algebra, but I wouldn't expect you to do this because I'm going to show you how to use it and solve it on a calculator, because you don't have to change it back into a log if you solve it on the calculator, okay? I'm going to teach you that. Now, this would come out front. You'd have x times log of 7 equals log of 8. And then, folks, just divide both sides by log of 7. X would be the log of 8 divided by the log of 7. And you would round that to 4 decimal places, yada, yada, yada. So, but I'm going to show you how to do that on the calculator, and you can do it a lot easier. Clear, okay. So type the first one in, 7 raised to the x, and then 8, okay? So I got the left side of the equation in y1, right side in y2. And I'm just going to hit graph because I don't know what my limits are. And I'm going to hit zoom 6, okay? All right, when I done that, it showed where they intersect. That's what I'm wanting. Now, I need it said 4 decimal places, right? So let's go over here and hit mode. And I've got it at 4 already. If you don't, just arrow down and go over and make sure you're over the 4 and hit enter. Boom, there you go. You've changed it to 4. Second mode, and then hit graph again. So second trace, number 5. I'm going to move that up a little bit. Enter, enter, enter. and you have an intersection of 1.0686. So the answer would be 1.0686. Okay, and if you've done this on the calculator, you would get the same thing. Okay, as far as if you solve the log of 8 divided by the log of 7. So I could show you that. Let's quit. So let me go log of, what do we have first? 8. Okay, of 8 divided by the log of 7, and hit enter, and we get the same thing. So it's a way to do it without a calculator, and the calculator allows you to be able to solve an exponential by looking at the intersection as opposed to having to change it over into a log. So that's the whole premises of why logs come about. It helps you to solve exponentials that can't get the bases to be the same. Okay. Now, would I expect you to do what I've done in the red, yellow, red, green, and blue? No. I would expect you to do it on the calculator. But if you want to do it algebraically, knock yourself out. Okay. You don't have to. It's easier to do it by the calculator and find the intersection. All right, same thing here. We're just going to do it by the calculator, right? So 2 to the x plus 2. So I'm going to hit here. We'll clear out. 2 raised to the x plus 2, and that's all up in the exponent. And then I got 9, so 9. I'm going to hit graph. I don't have a clue, but there you go. Zoom 6 limits still work. I have a line drawn at 9, so I can at least still see that. I want that intersection. Second, trace. 5, enter, enter, enter. When I do that, it's 1.1699. Now, note that when you have your calculator set for 4 decimal places, it's rounding for you correctly. So 1.1699 is the answer. There you go. Now, let's look at this one. The next two are dealing with exponentials that grow and exponentials that decay. And traditionally, you would solve them by logs, but we're going to do it by calculator. Okay. So if raw meats allowed to thaw at 50 degrees F, salmonella grows at a rate of 9% per hour. So you've got to look, that's a rate. That's R is 9%, which is 0.09. So if I do a base, that'd be a grows, so that's a growth, which is 1.09. So write a formula, amount of salmonella present after T hours if the initial amount is S. So S times 1.09 raised to the T. Okay. Now, health officials advise that the amount of salmonella initially present in the meat should not be allowed to increase by more than 50%. How long can the meat be left out to thaw at 50 degrees? Okay, so round your answer to the nearest tenths of an hour. So that would be R is 50%, which is 0.5. So 1 plus 0.5 would be 1.5, right? So make sure one thing before I do that. So I got to 1.5. Let's see. There we go. All right. So it's times S, the initial amount. Forgot the initial amount. All right. So I want to show you this because here's your equation, 1.5S, and go back over here. Finish this. So it's 1.5S, 1/2 times the initial amount, right? But we're gonna solve this, and I'm gonna show you how we're gonna solve it. We're gonna put it basically here. I'll just sort of be S times 1.09 T equals 5 times s. Folks got s on both sides. So really it's 1.09 t equals 1.5, right? And we're going to see that here when we look at this. The s is canceled, leaves you 1.09 t equals 1.5. And they're solving it by doing the log. So I want you to kind of look at that. They take the log of both sides and move the t out, and then divide, right? Kind of like what we've done on the example here 2 times ago. So, but I'm going to show you how to do it in calculator, and you'll be okay. So we're going to type the red in. So let's clear this. So clear 9 raised to the x, and then we'll do 1.5, and we hit graph, and we should see it cross right there. It's not going to be a tremendous amount there. Make sure that I got that as an exponential, yeah, graph. All right, second trace, 5, enter, 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 4.705. So 4.705, let's see, 4.705 nearest tenth of an hour, so it'll be 4.7 hours. There you go. Now, that's growth. Let's look at one that's decaying. Okay, concentrating of a certain drug into decreases by 20%. So that's a rate, 0.2. So base equals 1 minus R. So base equals 0.8. Write a function. Initial dose is 0.9 milligrams. So 0.9 times 0.8 raised to the t for time each hour. So times an hour, function of time. So that's the first one, right? That gave us initial concentration. Then it says the minimum concentration is 6 milligrams per milliliter. Or when should the second dose be administered? Okay, so 0.9 times 0.8 raised to the t equal to 0.6. And you could solve it by log, and I'll show you what that looks like. But we're going to put it in graphing calculator and let it do it. But I want to show you what that looks like. Here, dividing both sides by 0.9 and then taking the log of it and everything. So it basically comes out here, and they leave it as a log, right? Log is 0.6 divided by 0.9, all divided by the log of 0.8. You could type that in, and it would be correct because you're looking at a value. Now, I think it's easier to just go ahead and just say, okay, let's type this in the calculator and go from there. So clear that. Times 0.8 raised to the x, and then 0.6, and then hit graph. And in this decay, and you can see that it's decreasing from left to right. The blue graph is going down continuously, it's decreasing. And we see an intersect somewhere in here. So we'll hit second, trace, 5. Now I'm just going to move it. Enter, 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 and 1.8171. So now, tenth of an hour would mean that it's there. That one won't make that, so it's 1.8 hours. So that's kind of, sitting here talking about this. We use this in everyday life. If we take an aspirin, it says take one every 4 hours or so. They're looking at maintaining a certain level in your body so that it would be advantageous to counteract the effects of a headache or whatever is going on in your body. So that's when the drug companies are doing trials and stuff like that and drawing blood and stuff, they're checking levels and they're building their exponential, but they can use logs to solve it, and that's the properties of logs. So maybe this will give you a little bit better insight that you're been living exponential all your life because your body is an exponential, and you've been using logs because you got to solve it. So there you go. I'm on a hush, and I don't think we'll do. Yeah, we'll do that in the next video. But let's see. All right. I don't think I was going to do this one, but I'll show you how to write the equations. How's that? And then you can solve it. Sodium-24 is a radioactive isotope that used in a diagnosing circulatory disease. It decays into stable isotopes of a sodium at a rate of 4.73 decays, right? So it's going down, right? So that's a rate. It's a percent, so I got to do it as a decimal. So the base is 1 minus r, so that would be, I'm going to go out to 1, 2, 3, 4 decimals on that. So 1 minus 0.0473, ladies and gentlemen, that gives me 0.9527 as the base. Okay, that's the base. So a technician injects a quantity of sodium-24 into a patient's bloodstream. Write a formula for the amount of sodium-24 present for if S is initial. So S times 0.9527 raised to the T, right? It's per hour, right? Times in hours. Now, how long will it take for 60% of the isotope to decay? So round your answer to the nearest hundredths of an hour. So it should be raised to T equals, check it out. I'm pretty sure they've already gave it to us, but it's probably going to be 0.4 raised to T, but I don't want to tell you something wrong. Yeah, I want to make sure. Yeah, okay, so I was right. Yep, because they gave it to us as a rate. So I just want to make sure. So that's 60%. So the rate on that is 0.6. So the base is 1 minus, come on, 1 minus 0.6, which is the base equals 0.4, and of course 0.4 S, right? So the S's are going to cross out, and then I'm left with 0.9527 raised to the T equal to 0.4. If you put that Y1, Y2, you find where they intersect, you're good. Okay. When you're looking at decay, it says like 60% of the isotope to decay. Well, if you take away 60%, 40% of it's still there, and that's what you got to make sure you understand when you're doing decays. So, ladies and gentlemen, this ends Chapter 5, Section 4344, Part 2's video.